long time ago.
Hey, everyone.
Hello, good morning.
Hello. Is everyone on Zoom this morning?
Not everyone. Max is here, and we're waiting Mandela.
Okay.
And I've got coffee and a little marker. I'll stop the. Okay, remember me to record again. Okay, claims to be recording. So what I want to do today is get you more involved in modern notation. At some point, I'm going to show you kind of the alternative way of looking at this. And I think when I do that, I will probably, my picture just went away. That's interesting. Okay. Everyone still seeing me fine?
Yep.
Good. Okay. So what I'm going to do is eventually I'm going to probably photocopy a couple of chapters from other books. I want you to see an alternative way you can view all this. It's really, really weird. We're not going to do a whole lot with it, but I think you need to see that alternative method so that when you do pick up a book or take this course again for a second time, and I hope you do, if the professor uses that alternative notation, at least you'll have some introduction to it, because it's weird. It's just weird. Okay, so what did we do last time? Last time, the big thing we had, we talked about a dot product. We said our V is going to be what? This is V mu vector. These are the basis vectors. And we can look at the dot product of this guy. And so what did we say this is? This V, we wrote as this. Here's our dot. Now, how did we have to write the other fellow? This one.
A different index?
Yeah, you can't use the same mu. You have to use something different. We use nu for no good reason. Like this. Now, the V mu and the V nu are constants. I mean, just numbers. So I can pull those out like this. And you get this. And this right here we define to be something. What did we define the dot product between the basis vectors to be?
Eta mu nu.
Yeah, this is eta, lowercase mu, lowercase nu. And this is called your flat space-time metric. Okay, is that marker showing up fine for you guys?
Yeah.
Okay. When it gets too faint, let me know. Can you still read it here? How about this equation here?
Oh, that's a brilliant equation. Yeah.
I think so too. I created that one myself. Okay. Okay. So we said what happens is when we go to the geometries which are not flat, this is going to become G mu nu. So when our space is not flat, this right here is going to be G mu nu. And this is just going to be called the metric tensor. And that's going to be really important for almost the rest of this course. We're not quite there yet, but we're getting there. So let's go back to this guy here. So what we have here is when you have the dot product, you can write it like this. And what I could do is I can move these anywhere. So the way this is normally to get something else, and put this here. Like that. And what do we say this is? It's not really by definition, but we kind of left the class on that. What did we say about this combination? That's going to be V mu with a lowercase. So this is our contravariant. vector. This right here is our covariant. Yes, I get to put the word for in front. So dot product we can just as well write as v mu, or v mu, v nu, or eta mu nu, v mu, v nu. These are all equivalent. Does that make sense? And again, the reason why we had the lower one here, this is going to transform like the basis vectors did. And this one here is going to transform like the components of a vector. When I show you that new notation that you can do a little bit later on, maybe next week, I don't know when, we're going to kind of revisit what a lot of this stuff means. It ends up being equivalent, but it's a little funky. Questions? Now, what did we say the theta mu nu was? The theta mu nu, if I wrote it as a matrix, what does it become?
The identity, but with a -1 in the leading position.
Yeah, this one guy here, the 0, 0 position is -1. Everything else looks just like the identity matrix. That's what that looks like. And whenever you have this, it means you have flat space. And to give you heads up, what I mentioned is that when we go to our curve spaces, when you have this G mu nu, we're going to assume that our curve spaces at a given point look locally flat. So in other words, I might have a G mu nu here, but if I'm at a point and just look at the vicinity of that point, I'm going to have this guy here. But we don't know that yet, but that's where this is going. Okay? Now, a couple more things. Okay. We also have eta mu nu. Okay? And eta mu nu is going to look like this. An eta mu nu like this can actually convert a covariant vector to a contravariant vector. In other words, if you have this guy, that equals this right here.
So superscript and subscript are the same.
So it is the same as the other one, though?
It looks just like it, but the other case was this.
Yeah.
But this is how we can convert from one to the other. In flat space. So when we actually go to curve space, we're going to have G's here. And then this is going to be a little more funky than this guy here. You can see that this guy here, this is the inverse of eta mu nu. So if I do this guy, let's multiply these as do matrix multiplication here. This is kind of band notation here. Okay, there's no good notation here. By this, I mean, I'm writing this as a matrix, I'm writing this as a matrix. Don't worry too much about these guys here, the indices. This is bad notation here. And what crazy thing does that equal?
I'm gonna guess it's the identity.
Yes. That's what we get. So what I can do is now let's use grid notation. So if I write something like this, eta alpha mu beta. What do you think this is going to be? It's still the identity matrix, but we're summing on the mu's here. So we're left with what? We're left with an upper alpha, and we're left with a lower beta. So we're going to have an alpha up here and a beta here. Hey, what would be a good symbol for this? Right, this is going to be 0 if alpha does not equal beta. But if alpha equals beta, it's equal to 1. What would be a good symbol for that? Yeah, that's our Kronecker delta. So that's how we write the Kronecker delta from now on. Does this make sense? Now the upshot of this is what it's going to mean. So what do we write? V mu or V mu. What it really means is that this V mu here, if you write it, all the components here are going to be positive. So this would be V0, V1, V2, V3. Notice I'm using the lowercase here, but this lowercase here doesn't mean anything covariant, contravariant. It just means the components here. The contravariant part here is the fact that these are all positive. When I write this, what does it mean?
Explicitly have the minus sign in front of the V naught.
Exactly, you're going to have that guy here. So when you write these guys like this, so we said this is really our V mu, V nu, well, V mu E, mu dot V nu, E nu, which is our friend here. Our friend here, which is our friend here. What does this combination become? Okay, so this is going to be V0, V0. So what did that get from over here? This component times this component is minus V0 squared. Then V1, 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 V1 squared, and then V2 squared plus V3 squared. So the dot product between any two vectors is going to give us this type of structure here. Any two 4 vectors. Does that make sense? Now, sometimes in books, what does this part look like here? Remember, 1, 2, and 3 are really x, y, z. So this is vx squared plus vy squared plus v3 squared, vz squared. Normally, how would you write this in a book? It's kind of like v vector squared or like v squared like this. It's a 3-component thing. So sometimes in textbooks, what you'll see, when you have this guy here, you'll see this. You'll see that, or you might see like this. And this right here gets dumped into this guy here or this guy here. You'll see that a lot in textbooks. So this is often in textbooks.
That's just for like time. It's not like so many times.
Yeah, this is often in textbooks. You will see this. And does that make sense? To be honest, you just have to live with this handwriting for a while. This gets, it's not hard, but you can really easily get tripped up in this stuff. Very, very, very easily. That's actually one of the hardest parts, just getting the stupid terminology, the notation down. Questions?
Yeah, why was all this notation developed?
Oh, I think, okay, this is going to sound stupid. To make things easier. And it does eventually make things a lot easier. Although from this level right now, it doesn't look one bit easier.
Okay.
And when we go and actually look at this from another point of view, it's kind of called the as you know, there's the guy, the really well-known guy who just, got the Nobel Prize, Kip Thorne. Kip Thorne, so this is kind of the geometric way of looking at things. So I'm going to show you a math for this, which is kind of the geometric way of looking at this. And so in that case there, they refer to a lot of different objects here, and there's a reason for it. But it's not for ease. Whenever a new notation is introduced, it's always for clarity and for ease.
Okay.
You're first learning it, it doesn't look like clarity or ease.
That's good.
I have a question. Can you briefly go back and go through the argument of why the etas equal to Kronecker delta?
Sure.
We've already moved on from that.
Yeah, no, that's fine. Okay, so to begin, this right here is the inverse of this guy here. Okay, so now let's do let's say we had something like this. Okay, really what would this be? This would really be eta alpha 0, eta 0 beta, plus eta alpha 1, eta, not that at all, 0, but that's bad, 1, eta 1 beta, plus eta alpha 2, eta 2 beta, plus eta alpha 3, eta 3 beta. That's what that means. So let's say alpha does not equal beta. If this does not equal this. How do these look? These are actually diagonal. Remember, this guy here is that, and then this guy here is that. And so if this alpha here is not equal to 0, you're going to be off diagonal, you're going to get 0. If this one is not off diagonal, if this is not equal to 0, you're going to be off diagonal, you also get 0. So if alpha is not equal to beta, that guarantees that one of these is not along the diagonal, so this term has to be 0, and likewise for other others. Does that make sense? So this would have to be equal to 0.
Yeah, okay.
But if alpha equals beta, that means that alpha is either going to be 0, or it's going to be 1, or it's going to be 2, or it's going to be 3. If alpha equals 0, then this term contributes. -1 times -1 is 1. All the others are 0. If alpha equals 1, this is 0, this is 1, 0, and 0. Okay? So it's either equal to, in this case, you get 0. In this case here, you get 1. Does that make sense, Mike?
Yeah, that makes a lot more sense now. Thank you.
Okay, and that's why we can do it like this. And the reason for the upper one and the lower one is, again, when we look at these from now on, when we sum, the summing is always going to have an upper term, upper index, and a lower index. And then the result of this is the indices are what you're left with. So when you do this, we're left with an upper alpha and then a lower beta, which is why we have this guy.
Is it the alpha directly above the beta, or are we doing the thing where we give it a space?
On this one here, since it's not going to matter because it's diagonal. So this one here is always written one above the other.
Okay.
Because it's diagonal, so it's not going to matter. That makes sense?
Yes, thank you.
Okay. One other thing about this, the A's and the G's. So one more thing, and then I'm going to talk about things. So one more thing. Okay. G mu nu slash eta mu nu is a symmetric tensor. We'll find out more about why later on, but right now this is going to be a symmetric tensor. What does that mean?
Is it a tensor that's symmetric about the diagonal?
Okay, so what about the index? Indices.
You could switch the indices with each other and it wouldn't change anything?
Yeah, so this guy here equals this guy here. Likewise, you know, and since this is just a special case of this, it's the same thing here. We're going to get a lot of mileage out of that guy. Questions? Okay, let's get one more word result, and then we can start doing some other things. How does V mu prime, how does V mu transform under a Lorentz transformation? So in other words, we have this guy. That's how the contravariant vector transforms. The question is, what is the corresponding? Equation for V prime mu. And what I want to do is we're going to have an exercise in index manipulation. Okay, this one here is not going to be hard, but it's going to take practice it a lot. If you practice it, when you get it down, you're going to really, the amount of difficulties you can avoid in life can be large. But this is going to hurt a little bit. More than a little. Okay? We start here. Okay, how can I lower this index?
With the flat spacetime metric.
Tell me where the indices on that go. Up or lower? If I want to lower them.
Lower?
Yeah, so I'm going to multiply, I'm going to take this here. I'm going to multiply everything through by an eta. Now, let's figure out what the index here has to be. I want to sum on this guy here, so there has to be a mu here. Now I need another index here. Why don't I don't write this down? Why don't I just put a nu here and call it good? Don't do that. Why not? Because I have this nu over here. Okay. So I'm going to pick another index. So give me another good index.
C.
Okay. How about Ryan and Bradley? Why did you chime in? There's a problem with Mike's recording. He accidentally said.
Boy, did I hear lambda?
Clearly that was wrong. Okay. What?
Did I hear lambda?
Yeah, yes we can. Alpha, come on, guys. You go with something easy. Okay, Bradley would have said alpha. I'm convinced of that. Okay, thanks, Bradley. Okay, thanks, Bradley. So Bradley got it right. Okay.
Yay.
Now, what is this guy? This guy here is V prime alpha. Now, I want to lower this guy here, though. So let's figure out how to lower that guy. So how can I somehow want to have a V with a lower index here. So how can I rewrite this guy? So I want to rewrite this as some, let's say V beta. I want this to be something lower.
Multiplied by eta beta nu. We just do what we did again.
Oh, actually, we want to do this here. We're going to do a variation of that. Okay. Now let's actually, we want to get it like this. So let me put this over here. We're going to use one of our 4 tricks. Okay, so what's one of our 4 tricks? And I think Max already got it. Yeah, we're going to multiply by 1 in a clever fashion here. What's a clever way to multiply by 1? Kronos. So I'm going to rewrite this guy here. I'll write this guy here as eta as Kronos delta, beta, nu, V beta. Actually, beta, nu. Yeah. That's the same thing. Why is this equal to that? Because I'm summing up here. I'm summing on the beta. And the only term that's going to contribute to this is when?
Beta equals nu.
When beta equals nu. That's why this is the same as this. Does that make sense? Now, how am I going to write this alpha here? I mean, this delta here. I'm going to rewrite this guy. We had one way to rewrite this. What was it?
The 2 etas.
Yeah, we have to have the etas here. Now I want this fellow here to be a lower index, right? We want a covariant vector. So where do the index on this one have to be? Has to be lower. Now one of the indices has to be what to lower it? Beta. Okay. Now I need another index here. I'm going to call it sigma for no good reason. Then what does this one then have to be? Okay, there has to be the same sigma here. And then what's the last index here have to be? Nu. Right? This whole fellow here is delta nu beta. So now if I work this out, I get V alpha prime equals eta alpha mu, A mu nu, this guy, eta mu sigma. And this guy here, which is now my V sigma. And then the question is, what is this mess? so let's rewrite that. So this guy here, let's go through and figure it out. If I just give you something like this, if I covered this up, what would you say that does here?
That turn A into a subscript mu?
Which one?
The A?
The alpha, that's right.
Oh, okay.
Now, suppose I just
Yeah.
give you this. Well, what would that guy do? I'm summing in here. So what would it do?
Make it in a subscript sigma?
Exactly. Well, that's what we're going to do. This one's going to go here, giving us A alpha. This one's going to go here, giving me sigma. So what I'm left with is this. So this guy, and the other guy is this guy. So this is how our covariant, our covariant vectors are going to transform. This is how our contravariant vectors are going to transform. Now, that means, what on earth are these things? And I think we know what's going to happen here. We have daily homework too. Okay, so for Monday. Work this out. I'm going to give you a little push. Okay, so what are you going to do? Tell me what's, it's not going to be hard, but it's kind of a pain, which is why I'm not doing it. You have this here. What is this? This is nothing but matrix multiplication, right? We're summing on these guys. We're summing on these guys. This is matrix multiplication. So for Monday, what you're going to do is that you're going to say that this guy here is the alpha sigma element. Let's say is the alpha here, alpha sigma element from multiplying the three matrices together. Meaning it's this.
So is it still the identity with the -1?
It's not quite identity because of the -1 guy.
Yeah.
Yeah. But yeah. So what is this going to be? This guy here is the same thing as this. This is what? This is -1, 0, 0, 0. This guy is the same thing. What is this guy? Gamma.
Minus
Minus
beta
beta
gamma.
gamma. 0, 0. This is
Minus beta gamma. Gamma. 0, 0.
So you're going to work this out and get something like this. The elements of this matrix here are these guys here. And you're going to do that. Okay? Questions with that?
So can we just group the betas into the identity and multiply?
Can you do that? Can you take just this guy, times this guy, get 1, and then get basically this matrix back?
No.
No,
Order
because
matters.
matrices do not commute in general. Okay? But wait, there's more.
Thanks, Billy Mays.
I know, it's crazy.
Your resemblance is uncanny.
Yes. Yeah, this is what we're going to get. So that this right here is this guy here. Is this right here. I'm just doing this again just because I think it's good to see it again and again and again. All right, they're all equivalent. And this is a Lorentz scalar. What does it mean to be a Lorentz scalar?
It doesn't change under transformation.
Correct. This combination is not going to change under a Lorentz transformation, meaning I can say V mu, ooh, not that at all, equals V prime mu, V prime mu. Hey, but what do we know? How does this guy transform? How do we say contravariant vector components transform?
A mu nu.
Tell me why. Oh, okay, nu. Never mind. I got ahead of myself. Nu.
V nu.
And what is this guy? A. Where's the nu go? Okay. If I have a mu there, okay, where does mu go in here?
Mu goes in the superscript.
Okay. Now what? Well, we put a nu here.
Oh, no. Need something else.
Yeah, because this nu here is not going to be that nu there. Otherwise, we have a word sum. So we need something else. Give me something else. What? Alpha. Okay. Then V alpha. Let's rearrange these. These are just numbers. We'll have that better be. Remember, we have to get this. So what are the indices left here? We're summing on mu, so we're not going to have that left. We're left with a nu lowercase and an alpha uppercase. What had this better be such that this combination here is that combination?
Kronecker delta mu alpha.
Exactly. This has to be here, and decorate it for me. Where does the alpha and nu go?
Doesn't matter. Top and bottom.
Yeah, like that. So we have this, which is this. Okay. I can just as well put the nu there as y. It doesn't matter whether I use the alpha or the nu because I'm summing on them. So we have this fellow. That's really important. Now, is that quite in the form of matrix multiplication?
What you want.
Yeah. Is this matrix multiplication here? If I try to do matrix multiplication on that.
I mean, you could represent both of those as matrix.
You could, but it's a matrix multiplication in this form. What would you have to do?
Switch one of the indices or something.
Yeah, you basically, if there's a mu here, I have to get this mu down here. So how can I take these alphas and nu and then switch them so I can do matrix multiplication?
You need the space-time metric.
What?
Space-time metric.
Not in this case. So something more basic.
Transpose.
Remember, these are referring to the rows and columns, and I don't want to flip them.
Do with transpose.
Transpose. So I could just as well say that this combination here. I can say that this is A nu mu, A mu alpha. This guy's transpose. Okay, equals that. In this form, I could then write this in terms of matrix, a matrix multiplication. When you're doing matrix multiplication, the indices that you're summing on have to be adjacent. Now, in this particular case here, these are symmetric only in the flat space-time, so this doesn't matter. Does that make sense? Good. I'm getting a nod from Max. Good. You guys good?
I'm good.
Okay. There. Okay, so that's all the mechanics we have for a while. I'm going to show you another way to kind of reinterpret these, but not yet, because it's going to be weird. I want to start talking about some actually practical vectors that we get a lot of. So let's start getting some very common Lorentz scalars and vectors. So let's ask, what are some of the more important Lorentz scalars and vectors and four vectors that we will encounter? Okay, so one of them we know is already this x mu. Okay, so what is x mu?
CT.
X, Y, Z. Like that. Okay? Now, what do you think the following would be? So what would this be here? This would be if I drew a little diagram here. That would be this point here. So this would be my x mu. That would be a point in space-time. what do you think the following would be? Let's ask what is delta x mu?
A line in space-time?
It's gonna be, okay, so it'd be the difference between 2 points. So I have this point here. I call this x1, x mu1. This is x mu2, like this. And I can look at this little difference right here. Okay?
Can I use that stapler real quick?
Which one? Sure. No problem. There you go. Thanks. You're welcome. So this right here would be our delta x mu. So this delta x mu would be this guy here. So it'd be the difference between 2 points in space-time. That makes sense? So what that would really become would be, better write this as a matrix, C delta T, delta X, delta Y, delta Z. You can just leave it there. Thank you. You're welcome. So now we can define something. I can define delta S squared. How do you think delta X squared is defined? Yeah, this is going to be basically this guy here. Which is what? Delta X mu, B mu, delta X nu, B nu, equals. This is our eta mu nu. Like that. What do you think you're going to do with the difference between those 2 points? Yeah, we're going to let them become really, really small. So if we take the limit as delta x goes to small, we get ds squared equals eta mu nu dx mu dx nu. And this is right here, this is our space-time interval, right? And this right here is a Lorentz scalar. So this is going to tell us how 2 points in space-time are connected. You know, are they, you know, if here's a point and if here's a point, what's the distance between those 2 points? What's going to happen to general relativity? In general relativity, what does this equation become? What's the difference?
We're going to have a G mu nu.
That's exactly what it is. So when we go to general relativity, this is going to become G mu nu, dx mu, dx nu. And our space is going to become curved, so the distance between our 2 points in space-time are going to be all screwed up. To kind of give you like a little heads up on what's going on here, let's say you took the surface of a sphere. Let's say I'm just in this would be 2D space. Because it's the surface of a sphere, that's why it's 2-dimensional. And we're going to neglect time. So what would that mean here? That would mean that if here's some point on the sphere, if here's the first point, the second point is going to be like this. It's going to be that curved point. So in this case here, our ds here, okay, it's going to be the arc along here. It's not a straight line anymore. It's going to be that little tiny arc along here because it's connecting this point and this point. So our space is curved, and so this ds here is no longer a flat straight line. Because our space is curved and this g mu is going to be weird, we're going to get that little arc there. That's kind of where this is going. Does that make sense?
Neat. Yeah.
Okay, so what we're going to do with this, we're going to use our little friend here to start defining a lot of other things. But most of this course, what we're going to do, we're going to be taking this equation here and beating it to death. And everything else we got out of the relativity is really going to come from this fundamental equation. And this G is going to become, in the case of a rotating black hole, in the case of a rotating black hole, this is just hellacious. Okay, have a good day.
You too.
Thanks. See you Monday.
Yep, bye-bye. Make sense, Max?